Mastering recursive algorithms. From theory to practical implementation, recursion stands as one of the most powerful yet misunderstood tools in a programmer's toolkit. By allowing functions to call themselves, recursive algorithms elegantly solve problems that can naturally be divided into smaller subproblems. This technique is fundamental across fields ranging from data structures to artificial intelligence. The beauty of recursion lies in its ability to simplify complex tasks through repetition and self-similarity. Whether you're navigating trees, solving mazes, or generating fractal patterns, recursion offers a clean way to express logic that mirrors the problem itself. Mastering it requires understanding both its strengths and limitations. Understanding recursion fundamentals. A recursive function operates by breaking a problem into simpler versions of itself until reaching a base case that stops the recursion. This process resembles peeling layers off an onion, where each layer represents a smaller version of the original problem. Base case. Every recursive solution must define a condition that halts the recursion. Without this, the program risks entering an infinite loop, consuming excessive resources and crashing the application. Recursive step. In this phase, the function calls itself with modified parameters, gradually reducing the problem size toward the base case. This step embodies the core logic of the algorithm. Example: calculating factorials recursively involves multiplying n by the factorial of n1, continuing until n equals 1, which serves as the base case. Simplicity. Recursive solutions often mirror natural problem definitions, leading to cleaner and more readable code compared to iterative counterparts. Divide and conquer. Many recursive algorithms follow the divide and conquer paradigm, splitting problems into smaller pieces before combining their results. Caveat: while elegant, recursion introduces overhead due to function call stacks, potentially impacting performance for deeply nested operations. How recursive functions work under the hood. Beneath the surface, every recursive function relies on the call stack, a data structure used by programs to manage function invocations. When a function calls itself, the current state is saved onto the stack, enabling execution to return to the correct context afterward. Call stack mechanics. Each recursive call adds a new frame to the stack containing local variables and return addresses. Once the base case is reached, frames are popped off sequentially as the computation unwinds. Danger zone. Excessive recursion depths may cause a stack overflow error, especially in languages with fixed-size stacks like Python or Java. This limitation becomes significant when dealing with large datasets or deep nesting levels. Stack growth patterns. Understanding how your implementation grows the stack helps predict memory usage and identify potential bottlenecks early during development. Consider implementing safeguards such as limiting recursion depth manually or converting recursive algorithms into iterative ones when appropriate. Fundamental examples of recursive algorithms to illustrate recursion effectively. Examining classic examples provides insight into various scenarios where this approach excels. These include mathematical computations, tree traversal, and pattern generation. Factorial calculation. A foundational example demonstrating basic recursion principles. The formula n equals n times n minus 1 showcases direct reduction towards the trivial case of 0 equals 1. Fibonacci sequence. Although inefficient computationally, the recursive method highlights exponential growth characteristics inherent to many naive implementations. Optimizations like memoization become essential here. Binary search. Despite being implementable iteratively, binary search lends itself well to recursive formulations by repeatedly dividing sorted arrays into halves until finding the target element or exhausting possibilities. Trees and graph traversal. Recursive methods excel at exploring hierarchical structures like trees, inorder/preorder/postorder traversals, and graphs via DFS/BFS adaptations, simplifying complex navigation significantly. Merge sort. As a canonical divide-and-conquer algorithm, merge sort splits input into halves, sorts each independently, then merges outcomes, an ideal demonstration of top-down decomposition. Common pitfalls and how to avoid them. Despite its elegance, recursion harbors traps that novices frequently fall into. Identifying these pitfalls ensures robustness in software design and prevents runtime failures. Infinite loops. Failing to establish a clear termination condition leads to endless recursion cycles. Always verify that every recursive path eventually reaches the base case defined earlier. Unintended side effects. Modifying shared global states inside recursive functions can produce unpredictable behavior. Prefer passing immutable data structures instead. Excessive memory consumption. Deeply nested recursions risk overflowing available memory. Monitoring stack limits and considering alternative designs becomes imperative in such contexts. Debugging tips. Using logging statements or debuggers allows tracking individual steps taken by each recursive invocation, aiding identification of missteps quickly. Optimization strategies. Techniques like memoization cache intermediate results, preventing redundant recalculations commonly seen in naive recursive solutions. Evaluating performance considerations while recursion enhances code clarity. Evaluating its efficiency against traditional iterative methods remains crucial for high-performance systems. Several factors influence computational cost associated with recursive executions. Time complexity analysis. Assessing Big O notation reveals whether recursive approaches match expected asymptotic behaviors relative to alternatives. Some problems exhibit optimal speeds through recursive decomposition despite apparent overhead costs. Space-time trade-offs. Recursive implementations typically consume more memory than equivalent iterations due to additional bookkeeping required for managing call stacks. Case study. Tower of Hanoi. This puzzle demonstrates exponential growth in operation counts even though spatial requirements remain linear. The number of moves doubles with each disk added. Tail recursion optimization. Languages supporting automatic conversion, like Erlang, transform eligible tail recursive calls into simple jumps rather than pushing fresh frames onto the stack, mitigating some memory concerns. Advanced topics in recursive programming. Building beyond introductory concepts opens doors to sophisticated uses of recursion applicable across diverse domains, from game theory puzzles to machine learning models. Mastery entails grasping subtleties around mutual dependencies and nonlinear relationships. Mutual recursion. Two or more functions calling each other form mutually dependent chains. Such configurations arise naturally in modeling interactions between distinct entities requiring codependent processing flows. Indirect recursion. Unlike direct calls where function invokes itself explicitly, indirect forms occur implicitly through intermediary steps involving third-party components acting as bridges between recursive elements. Fractal generation. Mandelbrot sets and Sierpinski triangles exemplify visual representations achievable solely via recursive processes, showcasing intricate geometrical properties emerging from repetitive rule applications. Backtracking algorithms, used extensively in constraint satisfaction problems, e.g., Sudoku solvers. Backtracking explores possible paths, systematically reverting decisions whenever contradictions emerge. N-puzzle solvers. Sliding tile puzzles leverage recursive exploration guided by heuristic evaluations, illustrating combinatorial explosion challenges addressed creatively through informed search strategies. Real-world applications of recursive thinking far removed from academic exercises alone, recursive methodologies power numerous technologies integral to modern computing landscapes. Recognizing these applications reinforces relevance beyond abstract discussions. Data parsing. XML/HTML parsers utilize recursive descent techniques to navigate nested tag hierarchies efficiently, reconstructing document object models accurately reflecting source contents. Compiler design. Syntax analyzers employ recursive grammars to parse expression trees representing programming constructs, facilitating semantic analyses downstream in compilation pipelines. File system navigation. Operating system utilities performing directory walks rely heavily on recursive listings to traverse file systems regardless of depth encountered. Artificial intelligence. Decision trees implemented recursively enable rapid branching decision-making suitable for automated classification engines operating under uncertainty constraints. Dynamic programming. Memoized recursive variants accelerate optimal substructure resolution found prevalent in shortest path finding algorithms and resource allocation optimizations alike. Best practices for writing efficient recursive code. Writing effective recursive programs demands adherence to disciplined coding standards aimed at maximizing clarity while minimizing adverse effects stemming from improper usage patterns. Define clear base cases. Ensure all exit conditions fully encapsulate minimal viable scenarios, preventing unnecessary continuation past terminal states identified upfront. Prefer iterative alternatives where applicable. If profiling indicates performance degradation attributable primarily to recursion, consider rewriting affected portions using standard looping constructs. Use memoization judiciously. Caching intermediate results yields substantial benefits only when recomputation frequency exceeds storage overhead incurred maintaining lookup tables. Leverage tail call optimization features. Whenever feasible, structure functions amenable to compiler-level transformations, eliminating extraneous stack allocations entirely. Document assumptions clearly. Annotate boundary checks meticulously so future developers understand precisely what constitutes valid inputs accepted by your recursive interface definitions. Conclusion: recursion presents programmers with a versatile tool capable of tackling vast array of computational challenges gracefully. Through careful study and deliberate practice, anyone can harness its full potential responsibly. Embrace experimentation by attempting re-implementations of familiar problems employing recursive paradigms. Over time, recognizing opportunities where this style shines intuitively shall become second nature, enhancing overall proficiency dramatically.